Today's video is going to be looking at the graph or a table of f prime of x to determine what's going on with f. So we're going to use the graph of the derivative and use that to help us determine what our characteristics of our function is going to look like. So in your table of contents, this is just characteristics from f prime and f double prime. The standard is C3, and this is going to be on page 104 of your journal. These are the papers that you got today in class. It says students will use a graph and table of the derivative to determine characteristics of the function in order to identify the extrema and points of inflection. Okay, so let's kind of look and summarize everything that we've done so far with curve sketching. We're going to kind of summarize our justifications and look how everything is related. So at the top of your page 104, you have this table. So if we think about our function and the characteristics of our function, we think about things like our function increasing. We look at the critical values because those are where our maxes and mins are. Decreasing, concavity if it's concave down, our possible POIs, and then of course, one of those should say concave up. So let's change that really quickly. I believe on your paper that doesn't say down, that says up. So let's change that really quickly on here. And then looking at concavity, down, and then we use that also to determine relative extrema, relative minimum, maximum, and then of course points of inflection. So let's kind of summarize all of our justifications, because our justifications are how we prove some of these characteristics. Okay, so if our function is increasing, we use our first derivative to do that, and our justification for increasing is that our first derivative, or f prime, is positive. Okay, our second derivative tells us nothing about increasing versus decreasing. So I'm just going to put x out there because we don't use our second derivative for that characteristic. In order to figure out critical values, remember these are where our possible maxes and mins can occur. Our first derivative is either equal to 0 or it's undefined. So if our original function has vertical tangent lines, if it has a cusp, that's going to show in our derivative, and that's going to show up as an undefined value. Again, our second derivative tells us nothing, so I'm just going to X this out because our second derivative doesn't tell us our critical values. If the main function is decreasing, we say that our first derivative is negative. And again, nothing here. Okay. And then we use our second derivative to determine whether it's concave up or concave down. If our function is concave up, if f is concave up, our second derivative is positive. If it's concave down, it's negative. And if it's a possible POI, that means our second derivative is equal to 0, or again, it's undefined. But if we think about it, our second derivative is actually the first derivative of f. So f double prime is the first derivative of f prime. So we can actually use that idea as well because it kind of is a connection to our f. So if our first derivative was positive, let me get a different color. If our first derivative was positive, we said that our function was increasing. Well, if our second derivative is positive, that means our first derivative, we could think of it as increasing. It's kind of the relationship between our f double prime and our f prime is the same as the relationship between our f prime and our f, if we think about the derivatives, which means if our first derivative is decreasing, that means our second derivative, the slope of the slope, is going to be negative, and we can then say that our main function is concave down. And then our critical values, in fact, if we look at our first derivative, our POIs, or points of inflection, will actually show up as extrema. Okay, so it'll show up as a maximum or a minimum. Because I mean, that's kind of the same process we use over here. If we think about that relationship and that relationship, we're kind of just using that same idea based on our second derivative and how our first derivative is related to it. Okay. If we're going to identify our special points, if we're going to identify our local maximum, remember our justification for a maximum was that our derivative changed from positive to negative. But if we think about our function, that means our function is increasing and then decreasing. And that kind of makes sense because increase to decrease, that would make that the maximum if that was our function. Our derivatives goes from positive to negative. And our second derivative, remember we can use the second derivative test to determine a max-min if our second derivative was less than 0 at that value. So we had a maximum. That was that second derivative test that you guys learned yesterday during class. If we're talking about a local minimum, remember the justification for a local minimum was that our derivative changed from negative to positive, and our main function is changing from increasing to decreasing. Sorry, not increasing to decreasing, decreasing to increasing. But we could also use our second derivative test to do that. And if our second derivative was positive at that value of change, at that critical value, then of course we had a minimum. Okay, again, that was from our notes from yesterday. Now our point of inflection was based on our second derivative. If our second derivative changed from positive to negative, or from negative to positive, these work in both directions. If our second derivative changed sign, that means we had a point of inflection. But if we go back to the relationship from the top chart, that meant that our first derivative was going from increasing to decreasing, or decreasing to increasing. Again, that works in both directions. And what that meant for our function is that our function was changing from concave up to concave down, or vice versa, again, in both directions. Okay, so this kind of summarizes everything that we've talked about over the last week. Okay, and then we're going to look at how we're going to use this information to actually look at the graph of f prime or possibly the graph of f double prime. And what, depending on what information we want, is going to depend on what we look for on this chart. So let's kind of go to an example. So let's say we have a graph, and this graph is f prime. I always want to make sure I know what graph I'm looking at, my f prime. Now, the first thing I want to look at is my critical values for f. Remember, our critical values, sorry about that, moving the entire picture. Our critical values come from when our derivative is equal to 0. So if we think about the zeros of this graph, because this graph is f prime, our zeros are right here. So all three of those points are our critical value. Now, if we're looking for where our function is increasing on the first example, we're looking at increasing. Remember, the justification for increasing was that our f prime was greater than 0. Well, this graph is the graph of f prime, so our function, this graph, being greater than 0 means we're above the x-axis. So everywhere above the x-axis, we're actually increasing. That's positive. That's where our derivative is actually greater than 0. So if we go back to our chart on above, if we think about our first derivative and we're looking for increasing, we're actually looking to this column right here. We're looking, sorry, that was terrible. We're looking to this column right there. Okay, if we're looking where f is increasing, we're looking where f prime is positive. So going back to that one. Now if we look at our intervals of increasing, I could say that f is increasing on, remember we increase on intervals, not at. And if I look at the domain, my domain starts at -3. So it's not really starting at negative infinity, it's starting at -3. I always want to look at that. I don't care beyond the domain that they give me. So on -3 to -2, that's my first interval. Union from 0 to 2, and union, and I'm going to put the other one right here. Let me erase that really quickly. And from 2 to 3, because my domain again ends at 3. And of course my justification is always the same for increasing, is that my derivative is greater than 0. When I use my justification off of a graph, I want to make sure I use the function that they give me. Use the graph that's given. That's a really important thing for AP. If they give you the graph of f prime, whenever I justify my answer, I want to use f prime in that justification. Okay. I can also take this graph and put it into the number line that we're used to dealing with. So I'm going to turn this into a number line. Here. Actually, let me do one thing. Actually, let's not do that. Didn't leave myself a lot of room. Okay. So I'm going to put a number line. So on our number line, if we think about how we do this algebraically, we put, sorry, that should be a point. We put our critical values. So all I'm doing is taking my number line, my x-axis, and rising it to make my number line. Now if we think about it, in between, and of course this doesn't start at negative infinity, this starts at -3 and it goes to 3, so it doesn't go beyond that because of our domain. Now if we think about what I highlighted, we said that our derivative was positive there. Then it's going to go negative because it's underneath my x-axis. We're talking about this graph itself. Then it's going to go positive, and then it's going to remain positive in that region. So if we think about increasing, we can see our increasing in 3 intervals. Just like we did algebraically, all I'm doing is taking this graph and putting it into the number line that we're used to, which makes it a little bit easier because now I can say we have a max at x equals, and remember I'm looking where I'm changing from positive to negative, and the only place that happens is at -2. And I want to justify using my f prime graph, which is what I would use anyway. F prime changes from positive to negative. Now if we think of the slope at -2, that slope right here, that slope is actually a negative. So that's kind of talking about our second derivative test when we talk about the slope of this graph, because the slope of this graph is our second derivative. Because remember, the derivative is just the slope of whatever we're priming. Okay, so now I want to look at concave down, and that's where the table is going to help me. Sorry, let's go to that table. Because I'm looking for concave down here, which means I'm looking for here. And because I have my first derivative, I'm looking where my first derivative is decreasing. So I'm going to go back to the graph and look at where is this derivative decreasing. If we look at, and let me get a different color so I can outline that. If we look at from -3, we start, we're going to go down, decrease, 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 all the way till we get to that minimum value. Then we're going to increase till we get to the maximum, and then decrease again till we get to that minimum. Okay, so those are the two sections where I'm decreasing, where my second derivative is going to be less than 0, which is what our justification is for concave down anyway. So if I want to justify that, if I want to write that out, I could say that f is concave down on the interval from -3 all the way up till -1, where my red line stopped, union, and then from 1 to 2. And my justification, here I want to use my f prime. So going back to that chart, again, I'm looking here, and my f prime is decreasing. So that's the justification that I went. Since my f prime is decreasing. Okay. We always want to try to use the graph that's given to us for our justification. So they gave us f prime, so I'm going to use f prime to describe the actual behavior. And then, of course, the last one says, at what values of x does the graph of f have an inflection point? So a POI. Going back to my table, POIs, that was the way we justified from here. That's what told us we had a POI. And since I have the first derivative, I want to look at that. I want to look at where my first derivative changes from increasing to decreasing or decreasing to increasing. If I go to the previous one right here, possible POIs, I'm looking for the extrema on f prime, the max and the min. So going back here, if I look at where I'm changing from increasing to decreasing or vice versa, or if I look at the max or the min, I see I have a minimum there, a maximum there, and then a minimum there. So I actually have 3 POIs. So I have a POI at x equals, at -1, at 1, and at 2. And since, again, I was given f prime, so I want to use f prime for my justification. Since f prime has extrema. Or I could say since f prime changes from increasing to decreasing and decreasing to increasing. Either one of those justifications would work. This has less words, less letters to write. Remember, I always go with the short and the sweet version of our justification. Okay, so that's kind of how we read a table. And if we wanted to, we could actually create the second derivative number line by doing the exact same thing. That critical value, or that extrema value, that would be at -1. That would be at 1, sorry. And then that one would be at 2. And our second derivative, which is the slope of this graph, is decreasing. So a negative slope to a positive slope to a negative slope here and a positive slope beyond. So for our second derivative is just the slope of this. So what I'm doing is looking at the slope to create that number line chart, which helps us with both this and this problem right there. Okay, so I know it's a little mess and it takes a little while to get used to, but we'll definitely do practice with graphs because that's one of the big ways they'll assess you on an AP exam. Second way they can assess is given a table of values. So they give us a table of values and they say let f be a function that is continuous on the interval from 0 to 4. So again, here is my domain. I always want to know what my domain is. I'm not going from -infinity to +infinity. I'm going from 0 to 4. The function is twice differentiable except at x equals 2. And we can see that x equals 2. Our first derivative does not exist and our second derivative does not exist. If your first derivative doesn't exist, of course your second derivative is not going to exist as well. The function f and its derivative have the properties indicated in the table above, where D and E indicates that the derivatives of f do not exist at x equals 2. So the first thing I'm going to do is look at A. It says if x is in between 0 and 4, find all the values for x where f has relative extrema. Remember, I'm looking for two things when I'm looking for a relative extrema. I'm looking where my derivative equals 0 or undefined, and where our derivative changes sign. Okay, once I know that there's a sign change, then I'll determine whether we have a maximum or a minimum. So determine whether f has a maximum or relative minimum at each of these values. Justify your answer. Okay, so the first thing I want to look at, where my derivative is equal to 0. So for this one, I'm going to be looking off of this line right there. Okay, so my derivative is equal to 0 here. Okay, at 1. If I look to the left of 1, my slope is positive. If I look to the right of 1, my slope is positive. So there's no sign change, which means that is not a relative maximum or minimum. The next one I'm going to look at is that D and E, because undefined values can be critical values. If I look to the left, I'm positive. To the right, I'm negative. So there's a change in sign, which means if I'm going from positive going up to negative coming down, we have a maximum there. So I could say we have a max at x equals 2. Remember, go to the top line for the x values. And then if we look at our next x value of 3, it's negative 3. Our slope is negative 3. It's not 0, so it can't qualify as a critical value. Therefore, it can't qualify as a max-min. So I have a max at x equals 2, and I want to justify since f prime, I have f prime, so I can use it, changes from my positive to negative. Okay, and I'm done with that one. On B, which intervals is f increasing? Remember, again, we want to look where f prime is greater than 0 or positive. So again, I'm looking for that at that green line that I highlighted, and I'm looking at the intervals, not the x values. So I'm looking here, 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 and here. And I'm looking where my derivative is positive. So I see that f prime, or f, is increasing on my first interval from 0 to 1, union 1 to 2, again another increase, and then that's it. And I want to justify, so since my derivative is greater than 0, and I'm done. Now I wouldn't put 0 to 2, and the reason I don't want to do that is because at 1 I'm not increasing or decreasing, I'm not positive or negative, I'm actually 0. Okay, so that's why we have to split it up into two different regions. Okay, C asks for, let's kind of look at that, oh, not that. Okay. Hopefully everybody has that. Let's see if it'll let me, there we go. Okay, so C says, does f have a point of inflection at x equals 3? Explain. So point of inflection comes from the second derivative. So I want to look at the second derivative specifically at x equals 3. So going back to my table at the top, I'm going to actually look at my second derivative. So I'm going to highlight that one, different color. So my second derivative. So now I'm looking at the purple line. And I want to specifically look at x equals 3, which is that column right there. So if I look to the left, it's negative. If I look to the right, it's positive. So there's a sign change, and my derivative is equal to 0 there, or my second derivative is equal to 0. Therefore, it is a point of inflection. So let's arrow down. So I would say yes. I want to answer the question. Sorry. I'm making a mess here. I want to answer the question, so yes. f has a POI at x equals 3 since, and I want to be very specific, since our derivative at 3 is equal to 0 and that our derivative changes signs, our second derivative. Okay, I want to answer the question and really explain it. Okay, and then the last one, on which intervals is f concave down? So now we're looking where f double prime is less than 0 or is negative. So we're going to go back to our table and we're looking for those intervals of negative on our second derivative. So, I keep moving the actual sheet. So that interval right there, positive, we don't care, negative right there. So there's two intervals from 0 to 1 and 2 to 3. So I'm going to actually put those on here. So I would say get a pen first, concave down on intervals 0 to 1, and then union 2 to 3. And I know that since f double prime is less than 0. Okay. So whether we're looking at a graph or whether we're looking at a table, it all boils down back to those justifications that we talked about when we did it algebraically. So we're going to have a little bit more practice. In fact, we're going to have a couple of days of practice because this skill right here shows that you really understand the connection between f prime, and f double prime. So if you have any questions, go ahead and put them on your paper and we'll ask them first thing in class tomorrow. If you have questions, come see me in the morning.